Just to talk a little bit about 19 and 20. Alright, so ladies and gentlemen, if you look at number 19 first, it says to talk about temperature conversion, which means how can we take one temperature, maybe in Celsius, and convert it to Fahrenheit, or do the opposite, starting in Celsius or starting in Fahrenheit, convert it to Celsius. I think the directions are a little deceiving, like the wording of the problem. It says the formula to convert temperature from degrees Celsius to Fahrenheit is F equals 9/5 C plus 32. And then it says write the inverse function, which converts temperature from Fahrenheit to Celsius. It truly isn't like an inverse function because you're not going to switch, like literally switch the F and the C like we usually do. So I'm not going to make this C equals 9/5 F plus 32. Instead, you're finding the inverse by solving for the C variable, so that you should have a second equation that says C equals just by taking the current equation that's there and solving it for the variable C. So it's not a true inverse where you're flipping the X and the Y values, but Celsius and Fahrenheit are looked at as being like conversions or inverse types of way, like measures for temperature. So again, in number 19, you are not replacing or switching F and C. You're just solving for the C variable. So it isn't a true inverse where you're like going through the steps of finding the inverse. So you have to subtract 32 first, so that we have F minus 32 equals 9/5 C. And then how would you get C by itself? Yeah, so multiply it by 5/9. When it comes to a fraction, you never want to divide by a fraction. You always want to multiply by the reciprocal. Dividing by a fraction doesn't really help anything. But if you multiply by a reciprocal, and then you're reducing the problem as well. So multiplying by 5/9 then converts this to C equals, so now it's in Celsius form. And that would be 5/9. And you could keep it as F minus 32, because if you multiply 5/9 times 32, you get like an ugly fraction, which is okay to have. But it's probably easier to take Fahrenheit and subtract 32 degrees from it, and then multiply it by 5/9 instead of having ugly fractions throughout the problem. So number 19, it's 5/9 and then F minus 32. So for the second part, it says what's the Celsius temperature? Equal to 94 degrees Fahrenheit. So if I want to know what the Celsius temperature was, you would take 94 minus 32 and then multiply that by 5/9. And it's 30 something. 34.4? Yeah. There we go. So again, like I feel like the directions were misleading. Because yes, really, if you look at like the two, they look like inverses, the two equations. So I was multiplying by 9/5, now we're multiplying by 5/9 with the F variable. We were adding 32, now we're subtracting 32. So they look like inverses, but we didn't actually flip, like switch X and Y and solve for that value again. And then that's the same thing with number 20. So number 20 is talking about sales price, which we talked about sales price on Friday with the F of G of X, G of F of X. So a department store is having a store-wide sale of 20% discount. The price S of an item that has a regular price of R is found by saying the sales price is equal to the regular price minus 0.2 times the regular price. And the reason we're subtracting 0.2 is because that's the 20% discount that you're getting off of the regular price. So if we simplify that, R minus 0.2 R makes 0.8 R. So the sales price can be found by taking really 80% of your regular price. And that's what it means if you have 20% off, you're paying for 80% of something. So again, it says to write an inverse function. Okay. Thanks.
Actually, I think
Yeah, you might have to, yeah, in the front desk, yeah. So again, it asks you to write the inverse function, but you're not really writing a true inverse, you're just solving for the other variable. So you don't want to switch the s and the r, you're just getting r by itself. So if you had r equals the sales price divided by 0.8, or you could write it as 5/4 times s, if you had a fractional form. That would be okay as well. But the goal is for you to see like they really are inverses, because if I'm multiplying the regular price by 80%, that would give me the sale price. Or if I want to find the regular value, I would divide the sale by 0.8. So like the opposite, it's still kind of opposite or inverses of each other, because here you're multiplying to get the one value and there you're dividing. Questions? So the terming, like the words that they use, it should have said more like convert from one to the other instead of find a true inverse. Okay, that's good. I'll just take your. Any other questions with the homework? All right, so then if you will pass that forward, so I think then you were asked to find like the regular price of a sale price item that was $30-something, $38.08. So you just plug that in and get a regular price. So if you don't mind passing the homework forward then, please.
Well, they never got plastic.
Real talk, where is that?
I thought that was. I feel like I saw him this morning.
Oh, you know, he's there was like some kind of astronomy week.
Yeah.
I didn't get an astronomy in ninth grade. I'm just
Yeah. So he was in it, and like the elementary kids were coming over and they were doing
Where's Brandon? Brandon's been out for 2 days.
Bro, Brandon's down. I saw Brandon this morning. He was definitely in the trees.
I heard it was there. I just feel like.
He must be part of the astronomy club as well.
Definitely,
Yeah, I didn't sign his paper.
Ooh. You know what that means?
I'm telling the
That
lady.
homework is 0.
Yeah.
I heard it.
Miss Perry does that. If you're
Does she?
Yeah, for Miss today, like she goes out of her way to look to see if you turn it into gifts. Like that's kind of
Where'd he go?
I just take stuff out of the pockets.
Maybe I should get that into that.
All random is like 6 days.
All right, so in your notes packet, we are graphing today. So if you can turn to section 6.5, please.
I know it. I think I got 6 or 12.
Wait, I have.
I know, I'm sure you know, I feel like I know more.
Why? You work hard to get everything you want. You're not working hard at all.
Wait, why did you get her? Yeah.
All right, so you're on page 21 of the notes packet. And today we are looking at graphing square root and cube root functions. So essentially, if you can graph a square root, then any even root will look exactly the same. I mean, it might just be slightly like stretched differently, but it'll have the same shape. So if we graph a square root, you could graph a fourth root, a sixth root, an eighth root, and so on. So we're only going to look at graphing square roots. We're not going to graph every kind of even root that we work with. And then same thing with cube roots. So if you graph a cube root, any odd root you could also graph because the shape will be the same, the method or the process you would use would be the same. So we're just going to look at square roots and cube roots. We will be graphing them by hand with the aid of a little t-chart and some of the properties that would be going on with what's inside the square root or the cube root. We're first just going to look at a basic one. So that's what a parent function is called. So a parent function of the family of square root functions. So we're talking about f of x equals the square root of x. A parent function is the basic equation. It doesn't shift, it doesn't have any numbers in it, it doesn't move up and down or stretch left and right. It's just the very basic equation. Usually that's where you start graphing to get an idea of what the shape is. So if we were graphing for f of x equals the square root of x, we're going to make a little t-chart. When you have a square root, what numbers must be in the square root? or what numbers can't be in the square root. So what numbers can't we have in any of the square roots, Scott? Negative numbers. So when we're looking at making a t-chart, usually we use -2, -1, 0, 1, and 2.
You can't do that.
We can't do that because we can't use -2 and -1. And also, if we have a square root, we want to pick good numbers that you can take the square root of so that you get a nice whole number as an answer. So we're not just picking any random numbers, we're actually going to do a little bit of thinking as like what numbers should be good that we choose. So what's the first number that we could plug in for the square root of x? A 1. Even before the 1, you could plug in a 0. So 0, the square root of 0 is 0. The square root of 1 is 1. And then what would be another good number for x to put in the square root?
10.
4, because the square root of 4 is 2.
14. 16.
We're gonna stop there. 3 is good.
All right.
Yeah, but you're right. We could use like a 9, a 16, but we can stop there. So if you want to graph yours,
We're supposed to write a 4 and an X and a 2. And a
yeah.
1.
Well, my Apple TV doesn't like me today.
Yeah, Apple TV's teachers don't like teachers.
Yeah,
That's a good point. Yeah, that's a
it's not feeling.
My Apple TV in my house.
I guess it's because there were like 100 Apple TVs in the building. I don't know.
I think it was 5th grade when we got all new stuff. Like we changed our chalkboards to whiteboards and stuff like
It
that.
was like
I'm so
Oh,
grateful.
that's
Yeah, I'm so grateful for that because
As a teacher, I don't like chalk either. I did not like chalk whatsoever. All right, so this is what our graph should look like. Try and make it a nice, smooth, arched curve that kind of just moves to the right. So it starts at 0, 0. It can't be anything less than that because you can't take the square root of a negative number. And then yes, we could make it larger, but we only have so much space on the graph. So instead of filling in the blanks, what would the domain and range be in interval notation? So looking at your graph, interval notation for the domain, Chelsea.
0 to positive infinity.
Right, 0 to positive infinity. So the x value starts at 0, it goes to positive infinity, and then Chelsea, your y value?
0 positive.
Also 0 to positive infinity. So the lowest point on the graph is at 0, and then it's going to continue to get higher as we take square roots of larger numbers.
why don't
So
we ever do anything with the range?
we just did. Because
On a normal basis.
on a normal basis, because the range you must be looking at the graph in order to get the range, whereas the domain you don't need the graph. So that's why we kind of avoided it because we haven't really been looking at a lot of graphs. Other questions? All right, so square root graphs. Get it in your head that they're like a little hook. They hook to the right. So a little nice arch that's arching to the right. The other type of function we're graphing today, and it's just these two, is the cube root of x. So just like we did before with the square root, I'm going to make another t-chart.
I love teacher. I just think I love them.
I like tea tree oil.
Teacher.
Good for you.
I just made
That's what I think.
All right, so how about some good numbers to plug into the cube root?
0, 1, 8.
So 0 would be a good number.
Oh, you could also
Oh, we're doing negative.
do -1.
You could do a 1 and a negative 1. So the cube root of 0 is 0. A cube root of 1 is 1. The cube root of negative 1 is
Is negative.
negative 1. So you can take cube roots of negative numbers because negative 1 times negative 1 times negative 1 makes negative 1. And then the other cube root that we could do, I heard an 8
Good job, Chelsea.
and a negative 8. So the cube root of 8 is 2. The cube root of negative 8 is negative 2. Now I know your graph isn't large enough, but I would like you to make it larger. So put 3 extra tick marks on your graph so that we can fit that 8 and negative 8 on there. It makes it both, x-axis. So left and right. Add 3 tick marks to the left, add 3 tick marks to the right. Makes it a little easier to kind of look at the curve if you have that extra point instead of just having 3. So we're going over to -8. And up to 2. How about down to -2? Not up to 2. Over to -1 and down to -1, 0, 0, and then up 1 over 1, and then 8. Yours fits on there nicer than mine does. So again, your last point, mine would be off the screen. I can't write any further. But make sure you have that last point counting over 8 and up 2. So when you connect this graph, if you start at the 0, 0, that's like the center of the graph. That's the middle point of the graph. And connect them arching right, just like we arched to the right with the square root graph. And then if you go back to 0 and connect the other points moving to the left, it kind of makes, like it looks like a, kind of like an S, like a spread out S, like a flattened S. This is the graph of the cube root. So a square root only has the right side because you can only take the square root of positive numbers. But the cube root has two sides of it because you can take a cube root of a negative and a positive number. So that's why it has the two sides left and right of 0 on the graph. Questions? Okay, so we are going to do some skipping. So,
Not galloping?
not galloping, not literally skipping. We are going to skip example 1, math note skipping. We're going to skip example 2,
Oh no.
and we're going to skip example 3.
Oh my gosh.
Don't worry, they won't be on the notebook quiz, so like we're just skipping them. I want to be able to actually graph some good graphs and not some of the other basic graphs that are on there. So this should now be like, I don't know, is it halfway down your page?
It's pretty much just down there.
Yes.
Yeah, so at the bottom of page 22, it says the graphs of radical functions. So the graphs that we will be looking at will have a number in front of the radical, and then they have that h and k in the problem. And we worked with h and k when we did absolute value. We had absolute value of x minus h plus k. We also worked with h and k when we had parabolas. Remember, it was x minus h squared plus k. So the h and the k, remember, moves the graph left or right for h, up or down for k. So we've used h and k. We're going to continue to use that in the other 3 or 4 graphs that we'll be looking at for the rest of the year. So to graph it, the first thing says sketch a graph of a times the square root of x or a times the cube root of x. Well, we're going to kind of skip that step as well. But what I need you to think about, instead of sketching an actual graph, is to the shape of the graph. So anytime you see a square root, you need to think that it's this like graph that's arching to the right. Anytime you see a cube root, you need to think of like that stretched out S that goes to the left and the right. So we won't physically sketch a graph, but we'll make like a little picture so that we know our end result should look something like one of those two graphs, depending on if we have a cube root or a square root. Step 2 says translate the graph horizontally, h units. So h moves the graph left or right, and vertically k units, k moves the graph up or down. But there was a little trick that we had to remember. So if you look underneath, does anybody remember what had to happen with that h value?
Opposite.
Yeah, it moves the graph opposite. So remember, the h was always the opposite of what was underneath the square root or the cube root or the square or the absolute value. So it's always opposite for h. So underneath it talks about a critical point. The critical point is usually that one important point that you get from the equation. And it's always going to be given in the equation for you. Anybody remember what that critical point is? What letters would it be? What letters are in our equation?
H, K.
H, K. Thank you. So the critical point is the one point that we're going to draw from the equation. The others we'll have to come up with on our own that create our t-chart so that we can graph. But it's based off of the h and the k in the equation. So there are 4 graphs on the next page, and we're going to see if we can just work through those 4 graphs together. The first one starts with the square root, and then the second one is the cube root. But you see that there's a number in front, so there's a 3. And then we have the square root of x plus or x minus 1, and then we have a plus 2. So before we graph it, just kind of think square root, my end graph should be a hook graph that's kind of curving to the right. So that's what it should look like. So when you graph it and you plot your points, if it doesn't look like a hook and you have like points that are up and down and all over the place, then you probably did something wrong with your calculations. We will be finding the domain and the range eventually, but we're going to get those after we graph it. So we're going to make a t-chart. The first point that we're going to get in the t-chart would be the critical point. So if you look at the equation, what is the critical point from the equation? Josh?
1 and 2.
Yeah, so 1, 2. So positive 1, even though there's a negative there, the graph is actually moving right 1, opposite for that value, and then it's moving up 2. So 1 to 2 would be the critical point. Now here's the part that's a little different. We're not just going to pick 2, 3, 4 other random numbers. We need to pick numbers that work for the square root. So underneath the square root it says x minus 1. So the next number I choose needs to be something minus 1 that creates a perfect square root or a perfect square. So what number could you plug in so that you're taking the square root of a perfect square? Isabella?
5.
So why 5? That's good.
Because 4 is
Right. So if we plug a 5 in here, 5 minus 1 makes the square root of 4, and we can take the square root of 4. There's a number in between 1 and 5 that we could plug in. What would be another number that we could plug in, Chelsea?
2.
2. Why 2?
There's 2 minus 1 is 1.
Right, so we could also take a 2 because 2 minus 1 is 1 and the square root of 1 is 1. So we only need 3 because it's only half of the graph. So 3 points are plenty. We don't need any more than that. But the numbers you're choosing for x are the numbers that you would plug in and then take the square root of making it a perfect square. So we're not just picking random numbers now, we're thinking which numbers make it a perfect square. So now we're going to plug in those 2 values. So we have a 3, the square root of 2 minus 1, and then it says plus 2. So Nina, what is the square root of 1?
1.
1. So 3 times 1 plus 2 is
5.
5. So when you plug in a 2, my y value is 5. Now we got a 5, so 3 square root of 5 minus 1 plus 2. So Scott, the square root of 4 is?
2.
3 times 2 plus 2 becomes?
8.
8. So that would be our second point. So now we have 3. The first one was given to us in the equation. The other 2 we chose based off of them being perfect squares, and then we plug them in to solve. So our first point starts at 1, 2. So over 1, up 2. And then we're going over 2, up 5. And then finally over 5 and up 8. So as you connect them, try to make it an arching curve that's smooth. You don't want it to be jaggy. And then you can just kind of continue it on as a curve. So looking at the graph, what's the domain of the graph? Where does it start for x? Where does it go? So Savannah, where does the graph start for our domain?
1 to 5.
Yeah, 1 to positive infinity. That corresponds with the x of the critical point. So your starting point for your domain is really the h value of that first critical point. Savannah, how about the range?
2 to positive infinity.
2 to positive infinity. And again, that's the critical point or the k value. So the domain uses the x of our critical point, the h, and the range uses the y or the k from the critical point. Questions? All right, so underneath is the cube root graph. So we've seen how now to kind of graph a square root graph. Let's try and do the same thing with the cube root graph. Cube root graphs are the ones that kind of look like stretched out S's. And we're gonna think about graphing it the same way. Except this graph has a left and a right. So we're gonna find the critical point, which is actually the middle point, and then we'll see if we can get some points on the left and the right of that middle point. So by looking at the equation, what would the critical point be? So Libby, what do you think the critical point is from our equation?
The critical point would be 3 and
Right, so it moves right 3, down 2. That goes in the middle, so 3 and -2. So now we're dealing with cube roots. So going back to our perfect cubes, 1 cubed is 1, 2 cubed is 8, -1 cubed is -1, -2 cubed is -8. So 1 and 8, -1 and 8, those are perfect cubes. Those are the numbers you can take the cube root of. So whatever number you choose for x, when you subtract 3, it needs to equal 1, 8, -1, or -8 for it to work, for us to be able to take a cube root of the number. So you need to ask yourself, what number minus 3 would give me a 1? Or what number minus 3 would give us an 8? So let's start with the 1. What minus 3 gives us a positive 1? Julia?
4.
4. Julia, what number minus 3 gives us a positive 8?
11.
11. So my two x values would be 4 and 11 on the right side of the graph. Because 4 minus 3 gives us 1, we can take the cube root of 1. 11 minus 3 is 8, and we can take the cube root of 8. So now doing the negative side, you need a number minus 3 that's going to make -1. So what minus 3 makes -1?
2.
So 2 minus 3 is -1. And then Katie, what number minus 3 makes -8?
11.
No, you're good. So we need a -8. So something minus 3 makes -8. Ethan, what'd you say? -5. So -5 minus 3 makes -8. So we're picking -5 and 2 because again, they make perfect cube values when you plug them into the cube root. So we're not just picking any old x values, we're picking specific x's that work for the problem. So now we have to take these x's and try and plug them in. So the first one says -2, and then the cube root of -5 minus 3, and then -2. So what's the cube root of -8? -2. So what's -2 times -2, and then -2? 2. So that would be the first value. The second one, we have -2, the cube root of 2 minus 3, and then -2. So the cube root of -1 is -1. So -2 times -1, and then -2 makes 0. So see if you can plug in those other two values. So you're plugging in a 4, you're plugging in 11 into the equation. So -2, cube root 4 minus 3, and then -2. Or we would plug in an 11. 11 minus 3, and then -2. So the reason we're choosing these numbers is because they're perfect cubes. You can take the cube root of 8 and -8. You can take the cube root of 1 and -1. So Julia, what other x or y values did you get?
-4 and -6.
-4 and -6. Any questions on that? So now that we have our 5 points, one that we got from the equation, the other 4 we had to pick ourselves, we're going to plot those 5 points. So -5 up to, +2, 0, and then 3, -2, 4, -4, and 11, which is 1 off the graph, -6. why does this graph look opposite? Chelsea? Right, so there's a -2 in front. So usually the graph curves the other way, but because there's a -2 in front, it's going to be the opposite. It still has the same shape, it's just that shape flipped, doing the opposite direction. Anybody know what the domain of this graph is? So look at the graph, left to right. What's the domain?
Hey.
Audrey, what do you think the domain would be? Left to right. How far does it go to the left? And yeah, -infinity to +infinity. So the domain would be -infinity to +infinity. What's the range?
Negative infinity is positive.
-infinity to +infinity. Every single cube root graph is always -infinity to +infinity because there isn't a number that you can't put underneath the cube root. So it'll always be -infinity to +infinity. So what I'd like you to do is to go down to the bottom 2 questions. I think the hardest part is making the t-chart, picking the x value that goes in. So I want you to see if you can choose x values for A. You need 5 of them when it's a cube root. Choose x values for B, that one's the square root. You need 3 with the square root. So cube root should look like that stretched out S. A square root should just be a hook to the right. So see if you can pick good x values. Just start there. Like what x values would we use so you can take the cube root of it? Or what x values would you use so you can take the square root of it? Thank you. Yes, so Scott, for A, what's the critical point of A?
2, -1.
You're so close.
2, also -1. I don't know.
What has to happen with the number underneath the radical? It moves in the,
Oh, -2.
yeah, so this graph moves left because that, even though it's +2, it moves in the opposite direction of what's underneath the radical, and then it moves down. So then when we choose values, the numbers that we need to pick for x, we need to be able to make a 1 and an 8 underneath the square root, a -1 and a -8 underneath the square root. So Cade, what number +2 would give us a +1? A -1. So -1 + 2 makes +1. And Cade, what number +2 makes 8? 6. So -1 + 2 is +1. The reason we want that +1 is because we can take the cube root of it. 6 + 2 is 8. Again, we can take the cube root of 8. And then on the negative side, anybody have the negative side done? Julia?
-3 and -10.
So she said -3, -3 + 2 makes -1. And then -10 + 2 makes -8. So those will be the x values that we're picking for the graph. And that's the hardest part. So choosing x values that'll make perfect cubes. Does anybody have the y values? Libby, what do you have?
I have -3, -1, -2, and 7.
Okay, so Libby, if we plug in a -3 + 2, that gives us the cube root of -1 - 1, I think this one should be a -2. Everybody okay with it, a -2? And then a -1, and then when we plug in a -1, is that a 0? And then when you plug in a 6, you get a +1. So when we graph this, we have -10, -3, -3, -2, -1, 0, and then 6 and 1. So it's like a stretched out S. You could pull the S. Domain and range. Every cube root graph has a domain and range of -infinity to +infinity. All right, so we just need 3 points for the square root. Ethan, do you know what the critical point is for this square root?
3, -2.
Again, you're so close. I agree with the 3.
Wait, what? No. 3, 2.
3, 2.
I
Yeah.
wrote that down, I just said negative.
Okay, perfect. And then Ethan, what next x value could we plug in? So underneath here, what -3?
7.
7 minus 3 gives us 4. How about one in between 3 and 7?
Oh, 4?
Yeah, 4. So 4 minus 3 is 1. The square root of 1 is 1. 7 minus 3 is 4. The square root of 4 is 2. So those would be two x values, 4 and 7. Anybody have their matching y values? Chelsea, what do you have?
2, 0, -2.
So 2, 0, and then -2. 2. So we've got 3, 2, 4, 0, and then 7, -2. Again, this graph is upside down because of that negative in front. So that's why it's going upside down instead of being the other way. All right, final graph here. The domain should start at 3 and go to infinity. How about the range? So look at your graph. What's the range, Chelsea?
-infinity
-infinity to 2. Because this graph goes down to -infinity, at lowest point it's hitting is -infinity. It's going up to the y value of 2, and then it's stopping. So it doesn't go any higher than the y value of 2. So you have 8 graphs for tonight, and then the rest of just is kind of like sprinkling in some other types of problems. The last group of problems is that like f of g of x, g of f of x kind of problems. I would like a volunteer to do 21. And wait, I think Nina and Chelsea, never mind. So,
Nina, I feel like I should go first because I feel like you're gonna do better, so you might